Hi there. Now for this question then, we had to prove by mathematical induction that for all positive integers n, that this summation of 2r minus 1 all squared, r going from 1 to n, was equal to a third times n times all of 4n squared minus 1. So in order to do this, what you'd have had to have done is first of all check out that it's true for when n equals 1. And that means just substitute n equals 1 in the left hand side, see what that summation comes to, and put it in the right hand side and check that they both come to the same value. So first of all then, for that step then, when n equals 1, if you substitute it into the left hand side here, you're going to have 2 minus 1, which is 1, 1 squared is 1, and then when you sum that, r going from 1 to 1, you're just going to have that one term, which is going to end up as 1. Substitute n equals 1 in the right hand side here, and you can see that 2 comes to 1. So the left hand side is equal to the right hand side, and therefore it's true when n equals 1. The next step is to assume that it's true for n equals some constant, which we'll call k. So that's the question of just putting n equals k in here and k in here. So if you do that, write in that you assume it's true for n equals k, and you've got that summation for r going from 1 to k equals 1/3 k times all of 4k squared minus 1. Now on this basis, we next have to show that if this is true, can we prove that it's true for n equals k plus 1. So we need to look at when n equals k plus 1. So we take our series here and r goes from 1 to k plus 1 of all of 2r minus 1 all squared. So in order to work with this idea here, we can say that this is the same as the sum of the first k terms of 2r minus 1 all squared, and then plus the next term, which will be the k plus 1th term. So that's when you substitute r equals k plus 1 in here. So I've done that there, okay? 2 lots of all of k plus 1 minus 1, and then the whole lot is squared. So the next step is to write in what this is. We have assumed then, if this is true, it's the same as 1/3 k times all of 4k squared minus 1. So can substitute that in there. If you do that and clean this all up, okay, then you get this here, okay? Now we need to simplify this, and what we're trying to do is eventually then get that this turns out to be 1/3, and wherever there's an n, it should be k plus 1, and here this will be 4 lots of k plus 1 all squared minus 1. So what I'd want to do then is just expand this out. If you do that, expand it out, you'll notice I've taken a third out the front. I took a third out the front because I wanted a third anyway, okay? So I forced it out the front. And then I've expanded that bracket, giving me 4k cubed minus k. Because we took the third out, I need to do 3 times all of 2k plus 1 all squared, which gives me 3 lots of 4k squared plus 4k plus 1. And then expanding this bracket, grouping up the terms, you can see we end up with 4k cubed plus 12k squared plus 11k plus 3. Now, I need to factorize this, and we can get a clue of how it's going to factorize just by looking at what we're expecting to get here. Remember, wherever there's an n, there should be a k plus 1. So I know that this should be 1/3 and then k plus 1. So k plus 1 must be a factor. So if we do that, we've got this here. 1/3 of k plus 1. And then I'm going to have a quadratic factor. And the first term in that quadratic factor has to be 4k squared, so that k times 4k squared gives me the 4k cubed. We know that the constant on the end has to be 3 because 1 times 3 gives us that 3. We need to get the term here. It's going to be something k. And if I look, for instance, to just check out and get this 12k squared, then I know I'm going to have one lot of 4k squared here. That leaves me with another 8k squared. So I'm going to need to have the k here times 8k. 8k is the value that's got to go in there to make that come to 12k squared. So if we just write that in there, that's 8k. Check it out, okay? You should be able to get that 11k there as well from this as a check. That's going to come from doing 1 times 8k, which is 8k, plus k times 3, 3k, 8k, 3k makes 11k. So we now want to just factorize this, change it really so that it looks like 4 times k plus 1 all squared minus 1. Hopefully, if we write that in there, it should check out. Let's see. I've done it here, and if you expand k plus 1 all squared, which will be k squared plus 2k plus 1, times it by 4, you'll end up with 4k squared plus 8k, but then you'll have 4, but now you've got subtract 1, that gives us the 3 there. So you can see it is true then for n equals k plus 1 if it's true for n equals k. So we just need to finish off now. So in the usual way, we know that if it's true for n equals k, then we've just proved that it's true for n equals k plus 1. And since we know it's true for n equals 1, it must be true for n equals 2, then 3, then 4, and so on. So it'll be true for all positive integers. So quite long, but I hope you are able to follow that. Okay?